Perfect. So until now, we saw the layman definition of delta sigma modulator, and after that, we also analyzed it properly. We saw the functionality of the integrator, and we also talked about the linearized model of the delta sigma modulator. And when we realize the linearized model of the quantizer, we look at it as an additive source of noise. We also saw that there is a delay which is required because the output of the quantizer will not be available that within that instance. So if that clock cycle is passing away, so we are dealing with samples anyway. So then we will be getting the output from the quantizer in the next clock cycle. So the delay is of one clock cycle is important, and yeah, over here the delay is pushed into the system, let's say a black box. So let's not talk about it now. So we also see the loop filter, and we said that we derived an output of a delta sigma, which is basically the signal transfer function times U of Z and noise transfer function times E of Z. And we said that signal transfer function is basically L of Z by 1 plus L of Z, and noise transfer function is the high pass behavior, which is 1 upon 1 plus L of Z. So this is something which is providing noise shaping to us. So we talked about it. So now let's start with this video, and in general we saw that a noise transfer function is basic. In general, we saw that the noise transfer function is basically a high pass filter with the coefficients chosen or selected so that the noise transfer function evaluated at z equals to infinity comes out to be 1. So what does this means basically? So which means that the DC gain of the high pass transfer function should be 0, and which brings us to the conclusion that h of n, I mean the sum of all the samples should be 0, because at DC the gain of high pass filter should be 0. And we also saw the impulse response, and we said that h of 0, regardless of whatever the filtering network we choose in the forward path. So regardless of that, I mean this was our loop filter. So whatever network we choose over here in our forward path, our h of 0 should be 1. And this is what this statement means, that NTF evaluated at z equals to infinity should be 1. So we are using this symbol for quantizer, and when we close the loop around the quantizer, then the quantizer basically it means that the quantized at the input of the summer. So we have our summer over here. I mean, I'm talking about this summer. So basically, when we close the loop around the quantizer, it means that it quantizes, I mean, the input of the summer and the output of the summer must be of the same kind. I mean, either analog or digital. I mean, they should not be analog and digital. I mean, what do I mean by this statement is basically, this is the quantizer, right? So the input, if it is analog, then output should also be of a same kind, which is also analog, but at the output we have discretized levels, and we can take this output sequence with discrete levels and code it into a string of digital words with finite number of bits. But what I want to mention over here is that when we closing this quantizer in a loop, because we are using this in a loop, so the if the input is analog, then output must be of the same kind. So that's what important over here is. And when we enclose the quantizer in a feedback loop, then essentially it can be thought of a memoryless non-linearity with a transfer curve which looks like a staircase. But to implement such a box in practice, we might think that we will detect in which level the input lies. So this is the input and we'll detect in which level it lies and then assign the digital word to that level. But we cannot feed it back as it is digital and our input was analog. As I said, the output and input should be of same kind. So this idea, we cannot feed it back. So we will not only need an ADC which converts analog input to digital sequence corresponding to, I mean, which bean or which level the input lies in, but we also need to take that information and generate an analog voltage using that ADC in the feedback paths. So basically, if this is Y, I mean, we have seen the structure of delta sigma, right? So if this input at quantizer is Y and output is V, then let's say if this is Y, so if it's analog, so the V should, which is going into the feedback, the output V is discretized, but the V going in feedback is should also be analog in nature. So we have not only ADC, but we have ADC followed by a DAC, which is going into the feedback path. I'm talking about the um, feedback path over here. So basically, if we talk about this output, so this is basically this digital sequence. So practically, the delta sigma loop, I mean, we are working in a loop. So we have a negative feedback loop. So we have a feedback. So practically, the delta sigma loop will look somewhat like this, where we have delta, we have summation, integration. I mean, we have sigma. So we have ADC, we have discretized output, but in the feedback, we have a delay and we also have a DAC, I mean, a DAC. So this output of a quantizer is a digital word, except that it is coming out of a very high sampling rate compared to the Nyquist rate. So, I mean, Nyquist rate tells us that it must be just twice or more than twice of the in-band frequency, but as we are in the case of OSR, so the sampling rate is very high as compared to the Nyquist rate. Also, we know that there will be finite number of levels in ADC. What do I mean by that? So, it must follow that the step or the staircase cannot go from minus infinity to infinity. It will saturate beyond a certain point. I mean, it will saturate beyond a upper limit and it will saturate below a lower limit. And both of the lower side as well as the upper side are depending on the number of levels of quantizer. So, I mean, what bit quantizer we are using basically or realizing. So then we talked about the oversampling noise, right? It was spread over a range of pi by 2. So when we are basically using first order delta sigma, so the noise characteristics can be seen or observed in a way of a high pass behavior. And we can analyze this using a behavioral Python model. And yes, so we had our quantization noise, and this is the case of where we were doing blindly oversampling. But then now we have a case where we have a delta sigma modulator, and now we can see our noise behaving as a high pass behavior, and at lower frequencies it is facing a high attenuation, and this is its stop band, let's say. And at higher frequencies, obviously, the density of noise is very large, but as we have already discussed that over here, we will be having a decimation filter, which will smooth out the curve, and which means that we'll average it out using a low pass decimation filter and downsample it. So basically the higher components will be gone away and we will be left with the sample or the signal band with a very clear input. So, but this is what the behavior of a noise will be there in the first order delta sigma. And then moving further, now that we saw the feedback loop can do wonderful things by making a poor quantizer, making look like a good one, we now think of getting more out of it. So first order modulator, we saw that doubling the OSR gives us increment of 1.5 bits. So from first order delta sigma, if we see the structure of first order, linearized structure of first order delta sigma, so it's basically we have some transfer function or in the forward path, which is an integrator, and we realize the quantizer as a input along with the noise source. So if we consider this whole as a green box, then yeah, okay. So if we realize this complete thing as a green box, then we have a input, we have discretized output. And what is this green box doing basically is it's just saying that we have additive noise source along with the input signal. So basically, this is the this is how we mathematically represent the green box. And we can think of it. So basically we have U of Z, we have E of Z, but now E of Z is 1 minus Z inverse of E of Z. So this is derived from this delta sigma modulator. And this equation can be realized in this way. So we have U of Z. Yeah. We have, in addition, we have 1 plus Z inverse times E of Z. And in the output, V of Z is basically the output, right? So V of Z is equals to the sum of these two. The sum of these two. So this can be realized in this way. And when we look at it in this way, so basically the model for first order quantizer, the output was simply some input plus E of n. But now instead of input, we have like instead of input plus E of n, the output basically in this case is some input, I mean some input plus some noise, which is not E of n now, but it is 1 minus Z inverse E of n. And when output was basically some input plus E, we got rid of the noise in the signal band by shaping it using a negative feedback loop. So uh, earlier what we were doing, so basically earlier we were shaping the noise, we were using the negative feedback loop, we were noise shaping, right? So we got rid of that noise from the signal band using noise shaping techniques and negative feedback loop techniques. So now instead of just E, we have 1 minus Z inverse time E. And so we can think of the green box as being U plus some error, which is 1 minus Z inverse times E instead of just E. And we can use the same negative feedback logic again to reduce the error further in the signal band. So error is basically to reduce the noise further. So again, we have the green box, we have the negative feedback loop, we have the delay, it goes to the input, we have a delta, and we have a sigma. So this is again the same thing. We are repeating the same thing once again. And when we represent this green box, when we open it up, so this was the green box, right? So now this and this. So these two are basically the same signals. So then we can represent it as a single signal going to this feedback and going to this feedback. So now we can sit and derive the complicated mathematical equations and prove it mathematically. Prove this whole box mathematically. Or else, based on our previous knowledge, which was basically our V comes out to be Y1 plus the additive noise. So earlier, what was V earlier? So if we, I mean, somewhere we can see the V. Um, so earlier it was U, I mean, not here. Where is the equation? Anyways, what I'm trying to say is basically earlier it was V was U plus some additive noise. Now it is basically Y1 plus additive noise. So this is the not like this is the previous knowledge we had from first order delta sigma. So then you based on this knowledge for this loop, we have a mathematical equation which is basically V is nothing but U. So basically this is the original input plus 1 minus I mean the noise transfer function for this, which is basically 1 minus Z inverse times 1 minus Z inverse times E. So this is the additive noise, and this is how we come across the second order delta sigma, where we have the signal transfer function, which is 1, and we have a noise transfer function, which is basically the square of 1 minus Z inverse. So basically it is a second order high pass behavior. And in this case, we have h of n as 1, minus 2, and 1. Previously in first order case, we had 1 and minus 1. So over here we have 1, minus 2, and 1, and the summation of h of n. So here also at DC we need 0 gain, right? So for that, the sum of all the samples of Z transform of the NTF must be 0. And regardless of whatever loop filter we are using, the first, I mean, h of 0 should be 1. And because, as we saw earlier, the NTF, when evaluated at very low frequencies, earlier it came out to be omega, but in this case, at very low frequencies, if we evaluate NTF, it comes out to be omega square. And thus, the in-band quantization noise is basically delta square by 12 pi integration of 0 to pi by OSR, and we square the magnitude of NTF. So basically omega square, which is omega to the power 4 times it's the function of frequency. So then this comes out to be this value, and from this we can say that doubling the OSR now implies reducing the N-band noise power by a factor of 32, which corresponds to 15 dBs, which means we are getting the increment in the resolution by 2.5 bits. So shifting from first order to second order sigma delta really is helpful, because earlier we were getting the increment of 1.5 bits, but now we have increment of 2.5 bits. So we can see the increasing order of modulation has increased in-band signal to quantized noise ratio significantly. And in other words, NTF is now a much better high pass filter, because NTF is second order. Firstly, it was first order in first order delta sigma. So basically, as we move to higher orders, the filter gets more and more close to ideal behavior. So yeah, that's how it is. So NTF is now a much better high pass filter behavior, and we can look at the quantized outputs of the I mean, if we look at the quantized outputs, the first order gain comes out to be 2, and the second order gain comes out to be 4. So this is how we saw the first order behavior will look like, but the second order behavior will look like this. So this is the behavior of NTF, and when we compute the total noise density of first order, not just the noise of in band, which is basically 0 to pi by OSR, but I'm talking about the total noise. So when we calculated it in the first order case, it came out to be delta square by 12 times 2, because h of n was 1, so 1 square is 2. But now for second order, we have 1, minus 2, and 1. So square of those is comes out to be some squared comes out to be 6. And then this gives us delta square by 12 times 6. So previously the noise was doubled, but now the noise is even larger. So as I discussed in previous videos, as we move to higher and higher order of delta sigmas, the output curves gets more complicated, but in the end, we are using a decimation filter which smoothens out all the higher components, and in the uh, signal band, which is of our interest, you can see there is a reduced noise, and we have analyzed this over here. So uh, it's a really nice results, and we can see those results using Python. So this was the noise for the first order delta sigma, and this is the first order delta sigma over here. This is something, the output of second order delta sigma, which is much complicated. But after using a decimation filter, or basically what happens to the noise is over here, we can see the noise for the first order delta sigma and second order delta sigma. We can see this is our signal, right? This is our signal over here. This is our signal. And you can see it is 10 to the power minus 17 dB somewhere around. And over here it is 10 to the power minus 16. So we can see a significant reduction, or we can see a significant attenuation for the noise provided due to the high pass behavior around our signal band. So the noise around our signal band is significantly reduced, which gives us a very better signal to noise quantization ratio. So shifting to higher order delta sigmas is, I would say, a really good idea. And we will talk about it in great detail in next video. We'll generalize the delta sigma modulator, and we'll do it in next video. But as of now, for this video, that's all from my side. Thank you so much. And if you have doubts, do let me know.